Welcome to Whiskey Friday, a new adventure for us. We're going to move into a more produced video log style. We have a guest, our very first guest, which I'm very excited to have a great discussion about aerodynamics, is Mr. Ryan Neff, co-owner of Zebulon MSC Limited Motorsports Consulting. Is that
Yes.
MSC? Yeah, right on.
Mm-hmm.
And we're going to have a bit of a deep dive into aerodynamics. Not specifically about GT cars, but we will use GT cars, GT Porsches as the examples of the specifics around making the cars faster. But the concepts apply to just about any vehicle that has a contact patch of a tire on the ground if you want it to stick more. It can also technically work for an airplane or a submarine or a number of other things depending on what it is we get through and what we're talking about. So we're going to just kind of, this is pretty free form. We're going to ask some basic questions, and most of them from an engineering standpoint are basic with a giant trapdoor and rabbit hole, depending on how in depth you want to go in the answer. But we'll try and keep it moving. The idea of this is to record it, get this out into the world for folks to digest, and then come back for a live segment where we will answer questions specifically for folks after a few weeks of this being out. So welcome, Ryan. Why don't you tell us a little bit about yourself and why we should believe you?
Well, thanks for the introduction. I'm excited to do this with you guys. I founded Zebulon with my brother. We're both performance engineers for IMSA teams, WEC, kind of all kinds of different racers. But we wanted to bring some of that tech down to you and I, and then aerodynamics kind of became a very natural thing for us because it's interesting and it's a really dynamic way to add a lot of grip to a car. And honestly, it's kind of the in thing right now anyways, so it's just pretty cool. I don't know why you should believe me other than that we've been doing this for a long time, and
well, you've got some pedigree.
Make cars go fast.
You've got some pedigree.
Sure,
you've got a number of teams. So Ryan's being very not coy, but humble. There we go. Yeah, that'll get edited. There we go. He's been a part of a number of winning Carrera Cup teams for a long time across a number of cars. He's been a part of podium winning, top shelf winning. His brother has been a part of the design of some high-level marquees bespoke race cars. I don't know how much we can say about that in a public forum, but we'll just leave it there. He also currently is the lead race engineer for Corvette Racing, and they won the 24-hour Le Mans last year. So
yes, he did.
It's not like y'all are trying to break through into like grassroots time attack. You're literally taking high-level motorsports winning capabilities, design, et cetera, and trying to filter it down into kind of a usable street car version of what works for class-winning race cars.
Yeah, I mean, there's so many things that we've learned over the years, and we just don't see that make it to SCCA guys, to NASA guys, to time attack guys. There's a lot of technology that people already do have that they're using, but we wanted to put our own spin on that, and we just really like to win. I guess we have the competitive spirit. Yep. You can tell from kind of our track history that we just want to do a good job, and we want to help people go fast.
Right on. We'll throw some pictures of Corvette Racing and some of the JDX guys. If you let us know what era, what this, what that. I mean, you guys came in second this year, I think.
We were gonna in Carrera Cup we were third we got knocked out of one of the last
Your
races,
guys got punted. Yeah.
Yeah, I mean, Carrera Cup is a very competitive series, so
right.
The guys drive hard. They put everything that they've got into it. We're working in this teeny tiny little box of what we can change, and so when they're driving really hard, mistakes happen, and but we were there. We were in the hunt.
Right on. Let's start with just the most basic. What is aerodynamics?
So aerodynamics is the study of airflow and how it moves around surfaces and how it essentially adds force to those surfaces. So the easiest example of that is an airfoil. Doesn't matter where it is, if it's on a plane or a car or just by itself, how the flow field is moving around that body. So that's the basics of what aerodynamics are. And then as an aerodynamicist, I look at those flow fields and try to manage them and use them to our advantage in our specific application, which would be making race cars go fast.
Right on. Some about that. So we did a brief live last week trying to help some of the folks out there that might be investment bankers or captains of industry or doctors or whatever they might be, that don't necessarily haven't gone through fluid mechanics, haven't necessarily understood that air has mass. They might understand it from of course the air weighs something, but the reason this can translate into performance and that air can put a force on an airplane wing or onto a car is because air has mass, and through its mass therefore has momentum, and you can manipulate it in advantageous ways, either lower pressure or higher pressure, and using those aerodynamic devices to kind of tailor what you're looking at. And from that standpoint, the next thing that we're going to try and define, and we're going to kind of step through this, we're obviously not trying to teach anybody how to become an aerodynamicist, but at least understand what it is they're looking at and why they should want to do this. Downforce and drag is something that you hear a lot about. There may be plots, there may be specific things like very early on when I was learning about aerodynamics, I would see this ratio L over D, and for race cars it might be negative L over D versus an airplane L over D. Explaining some of the vernacular so we can kind of give our folks a basis of, so we don't have to continue to define it as we keep going through the rest of the talk. So downforce and drag are used for people to try and comprehend, is this aerodynamics good, bad, efficient, inefficient, these kinds of things. Talk to us a little bit about what is downforce and what is drag.
So downforce is negative lift. Lift being the lift force that an aerodynamic surface can generate. In a race car, we flip that upside down and it's negative lift. So when we say lift over drag, it's negative lift over drag. And so lift is that vertical, or that vertical force of aerodynamic loading. Drag is longitudinal. So as a car is moving through the air, or any body is moving through the air, it's generating a drag force that is resisting its motion. Okay. So when we say lift over drag, that means the ratio between how much lift we're generating, or negative lift, and how much drag we're generating. So a more efficient aerodynamic surface has a higher lift to drag, or in our case, a lower lift to drag, because it'll be negative lift.
What are some examples of an efficient L over D? Like, is it ever like 90%? Is it, are they single digit percentages? What's good, what's bad, kind of thing?
That In the world of racing, there's a very wide range of
Okay.
lift to drags that are attainable. So there are some race cars out there that theoretically are 10 to 1. There's really not any professional race cars that are that high right now, but
Like even Formula One?
Formula One could be around there.
Okay.
I don't know enough about very specifically what the Formula One cars are right now to say exactly what they would be.
Yep.
But in like the WEC or in GTP, the organizers have actually outlined a target lift over drag ratio. So now all of those cars, it's part of their BOP. They just design the car to a lift to drag ratio that's mandated. And that's why we get to see all of this really cool, interesting stuff happening, both in the prototypes and even in the GT race cars, in the GT3 spec cars.
Yeah.
So everybody's kind of designing to a target now. In your and I world, our world down here, we can do anything that we want. We can target anything.
It's unlimited. So we can do anything we want, right? Yeah.
So
quick aside. Go ahead. Go ahead.
I was just gonna say I could see some GT cars, some full body cars getting to 5, 6 to 1 lift to drag relatively easily. It's dependent upon a lot of things. It's hard to say without doing the testing and the legwork.
Without getting all specific, getting the specifics down. Let's jump to the tire model and chart, because a lot of people they miss. There's a misconception that the aerodynamics make the car faster. The aerodynamics alone don't make the car faster. It's what they're doing, what's happening at the tire interface with the ground that makes the car faster. So you sent us a chart, super clear. We can talk about that here for a second, because it is really a race car going fast around a racetrack has everything to do with how you're using the tire.
Yes. So the tire is the only thing that's actually touching the ground. It's the only thing that's transmitting forces from the road surface into the car and vice versa. So what we're doing with aerodynamics is we are augmenting how much grip the tire is able to generate.
Right.
So this chart, if you want to pull that up, I can explain it.
Yep.
This is a tire model. Cool. So you can see the bottom is slip angle increasing to the right, and the lateral force that the tire can generate is increasing vertically here. So first thing is we need slip angle on a tire to generate grip. Period. That's how tires work.
To explain slip angle, it's more the road is going kind of, if you're driving straight up the road, you turn the tires a little bit. The tires aren't necessarily going the direction you're pointing them. They're moving forward a little bit, and they're moving in the direction that you're pointing them at the same time. And is that what they mean by slip angle?
Yeah, so slip angle is very basically, if the car is going this direction, like if we're looking down on top of the car and the car is going this direction and we've turned the tires this direction, so the car is starting to turn and it's now moving this direction. But the tires are turned more than the angle that the car is actually traveling.
Sure.
That difference is the slip angle.
Perfect.
And so on this chart, that is kind of what we're looking at here, is how much grip is generated for the slip angle. And you can see there's levels here. So 400 pounds of load on a tire, 600 pounds of load on a tire, 800, 1,000. There's two ways to add load onto a tire: transfer weight to it, or just have more weight on it, or load it with a force, i.e. an aerodynamic force that is acting on the chassis of the car, going through the suspension and into the tire contact patch. So there's some benefits with that. If you just have a 2,500 pound car versus a 3,000 pound car, yes, there's more load going into the contact patch, and therefore technically generating more grip, but you also have to accelerate and decelerate that extra weight. Whereas an aerodynamic element like a wing or a splitter is relatively low weight compared to something like a big portly car, but it can add a lot of load to the contact patch. So it's kind of like free extra load on the tire. But it's relatively dynamic. You can see that the peaks of the maximum grip, which is that orange line, that is actually changing. And then you can see the step in how much lateral force you make with every extra step of load on the tire decreases and decreases and decreases. So this is why when you add aerodynamics to a car, if you don't have any aero, a car is generating lift, and then you add a little bit and it feels amazing because you've basically taken that lift away, and that first step based on how a tire generates grip is huge. It feels really good.
Right.
And then you keep adding more and more and more, and you generate a little less and a little less and a little less and a little less. So we're fighting that as we go.
So after kind of the first hit, so to speak, there's diminishing returns the more you add, because the tire can only accommodate an increase of slip angle or an increase in lateral force. Let me say this a different way. It's not linear between we add normal force on the tire and the lateral force that it can generate from adding more normal force. It becomes probably to the square or to the cube diminishing would be my guess.
That's all dependent upon the actual tire and the tire data. So one of the things is this chart is very theoretical. It's just drawn out to illustrate. If we were Formula One or something like that, or if we wanted to go spend a bunch of money, we would go and do a tire test.
Sure.
Yeah, we would go, we'd go and actually get a tire tested at a testing rig, or, there's on chassis rigs that some manufacturers have tested. Some manufacturers give you tire data, but that's pretty rare.
Sure.
So, there's a lot of implication with that. But on the whole, this is how it works. And this is why you see those diminishing returns and what we're battling as we add more and more and more aero loading to a car.
Awesome. Is to start going through the function of the aerodynamic devices. And I want to kind of, from our viewers and kind of our standpoint, helping them to understand that it's a system of parts, that it isn't necessarily I add this in any order that I want, then I add this in any order that I want. There is a well thought out progression as to why you add certain aerodynamic devices before others. So as we're kind of going through this, let's see if we can't help folks with not quite a buying guide, but more of a what can I add first that's going to help me, and then what should I add next, and et cetera, et cetera. So the first thing that we're going to talk about are canards/dive planes. They go by a number of names. And these are small devices that you would put on the front of the car to help with bringing a bit of the balance of pressure. And we'll talk about balance of pressure because that's a big reason as to how drivers can take advantage of the benefits of aerodynamics and how they're able to do things in a race car as we're kind of going through this. So why don't you tell us a little bit about what canards and dive planes are? What's their function?
So they function in multiple ways, really, but they do add downforce to the front end of the car. Very simply, they have a bit of a scoop shape or an airfoil shape that creates a small pressure differential, and that does add a little bit of negative lift to the front of the car. So that's the first little bit of it for sure. But that pressure differential, high pressure on the top, low pressure on the bottom, generates a vortex that rolls up along the edge of your dive plane, and that travels down the side of the car. And if you place these correctly, that vortex has a low pressure core. It's very high energy, and if you
Like a
place it correctly,
tornado.
you can, yeah, kind of. You can help that. You can use that to help extract flow from the wheel well. You can use it to help virtually seal the bottom of the car at the side skirt. So it does a lot of things that can help make downforce on the front end. It does affect things downstream of the car further down, but everything does. So typically there's a good balance there. The one thing you have to be careful with on dive planes is they can become very draggy, and they interact with each other a lot, and they can interact with your splitter a lot. So there are nuances that you have to be aware of and be careful of.
Right on. Some of what our customers look for, we'll just say everyone's an amateur driver that we generally interface with. There aren't very many getting compensated pro drivers that are driving GT cars for fun that want to modify them. They get paid to go drive really fast race cars, so they don't need to go drive a GT car for fun on the racetrack. They might, but they're going to drive it stock because they're a Porsche factory driver or whatever they might be. Most of our folks complain about understeer, and in our world, most of the time understeer is self-induced. They are doing things, asking too much from the front of the car. They're trying to turn it and stop it all at the same time. I've gotten this question forever. Will the dive planes eliminate understeer? And the answer is always kinda. It's not a single thing that will do it, right? Maybe, exactly. If you utilize it, then more advanced drivers see a bigger benefit from a dive plane than beginning novice drivers, because they're at a higher level. They can manage front grip in a more nuanced way, and can begin to feel the balance of pressure moving forward, the front of the car biting a little bit, especially at high speed, as is typically the case with amateurs. They drive the slow sections of the track fast and the fast sections of the track slow, and so they don't always see immediate benefit. That said, it is one of the first things that you can add to the car to begin your aerodynamic journey. As we're moving into, we'll say, more efficacious aerodynamic devices like splitters and wings, let's talk about what people may not immediately understand. I'll give you, for instance, it was not clear to me until I started working with you on CFD that the low pressure section of the wing actually set up an entire pressure field in the back of the car that would drive the bottom of the car harder. We create more differential pressure, and the whole bottom of the car and the entire surface area underneath of it begins to work better than just better. It begins to work in a more efficient way because of what we're doing with the wing on the car. And that was new. I mean, it became obvious once I saw it. I was like, aha, of course. But it wasn't obvious at the time when I was jerking around years ago buying wings for cars. So in that vein, can we talk about how wings, splitters, dive planes, when designed, we'll use the word properly, or in connection with one another, how you have to kind of dial all of these things in? That was a lot.
Sure.
So,
well,
sorry.
Yeah. No. I'm just trying to internalize all of this.
Crystallize that into a single question when it was 15 questions all rolled into one giant thing.
Yeah. Let me start with just kind of reiterating what I said with the dive planes and how it affects things downstream of the car. Mm-hmm. Everything you do around the car is changing the flow field and affecting things around the car. As a vehicle moves through the air, it's actually affecting the airflow, the pocket of air in front of the car, significantly in front of the car.
Mm-hmm.
So
like feet or meters or
multiple feet. It could be
Okay.
Even car lengths. Depends on the speed, right?
Yep.
Somewhat. But all of these things work together. And like you said, with the wing making its low pressure, and then that being a pressure area, an area of low pressure behind the car, we can use that to extract flow from underneath the car. When we add a front splitter to a car, we get better flow underneath the car. And on a P car like this, they're relatively flat floor, so there's some decent benefit by doing that. And so it all kind of works together.
Sure.
Like you're gonna get more from the splitter by having a really good rear wing than if you had the same splitter with a worse rear wing. And that's just because everything is kind of working together, and those pressure differentials are relatively far reaching. So I mean, it's sometimes not measurable, sometimes it is.
Let's talk a little bit about the wing wing design. There's some things that we'll get real nerdy here for a second about this. So there's attached flow, and then there's detached flow. Can you help people understand what that means that may not be engineers, and understand that there are boundary layers, and that the flow may want to stay, the air as it's coming around a shape may want to stay close to it, or it may want to start to fall away from it, and what the advantages and disadvantages of attached flow versus detached flow, or these kinds of things might be?
Yeah, so detached, well, so let's start with the boundary layer.
Yep.
Because you mentioned that. Think about a stream, and right at the bank, the water is flowing, but very slowly. And as you move away from the bank towards the middle of the stream, it's flowing faster.
Yep.
Airflow is the same. It's a fluid. It acts as a fluid. So along the surface of the car, the wing, splitter, whatever, that layer is building up, and that's what we call the boundary layer. So we get a thicker and thicker and thicker boundary layer as you move along the surface. So we have a functional limit on like wing size and how much curvature that you can design into bodywork and things like that before you get either very stagnant flow or the fluid detaches altogether. And it's relatively dynamic, and the flow can reattach if it's designed to, or even if it's not designed to. There's a lot to it, but in a sports car wing, we shoot for attached flow that then, when you adjust the angle very high, it's always going to start to detach or stagnate a little bit, but we want that to be like a gentle, controlled stagnation or detachment.
Okay.
I don't love detached flow personally at all, but it's just going to happen sometimes, and the flow fields around different cars are always variable, so you just can't control for that 100% of the time, which is why we want to design it for a gentle detachment. When you adjust... Sorry,
Ryan. From an engineering standpoint, is it reasonable to say that attached flow consumes less energy than detached flow? We're not allowing the air to become chaotic, and we're trying to maintain some level of order to the flow as it's going across the body that it's on. And by having detached flow, you're allowing I'll just get real nerdy, you're allowing the Reynolds number to increase to extent that it's now turbulent flow, and therefore potentially more draggy and less predictable what it might do, et cetera, et cetera. Is that one of the main differences between attached and detached, or do I have that way off base?
You're basically right on the money. So when we have a fully detached flow, we get flow reversion, everything. That's where the Reynolds number is very high, and
yep.
That's where
you get all the little curls off the back end. Of people have seen the smoke trails. You get all the curls kind of off the back of the car and that kind of stuff. Yeah.
And a lot of times when you have really bad flow separation, you'll have a hard separation on the wing, and that's what we call a stall. and that can add drag significantly and reduce downforce significantly. If we control for that and make it a little bit more gentle, we don't lose as much to drag. But in my empirical testing, you pretty much are always going to see a drag increase. Now, that may or may not be too much of a problem for sports car guys with street cars that have these wings, something like that. Typically, we're not running the angle high enough to really have super detached flow anyways. But if you are, you're already, have a lot of wing angle. And so you're getting a reasonable amount of drag because you've gone beyond the efficiency, the very efficient range that the wing is at.
That kind of stuff. Yeah, because that's good for guys to get it, because the next question is on here, rear wing function and why you would use a single element instead of a dual element, or under what circumstances would you start adding additional planes to a wing, and why is that advantageous?
So what I was saying before was a perfect lead into this, where as you increase the angle of attack on a single element wing, you go beyond its efficiency range, and you start to get into separation, flow separation, and stagnation, detachment. So a single element is very awesome for relatively middle levels of downforce, and when you're able to run the wing at an angle that is very efficient, they're awesome. A lot of times you're only allowed to run a single element in the rule set that you want to race in too. So there's definitely a place for single elements, and most guys are only going to need a single. A dual element allows you to get a much more efficient, significantly higher downforce setup, because with that second element, it essentially allows you to renew the boundary layer on the airfoil. So if we had a 13-inch or a 300 millimeter cord single element, and then we had a 300 millimeter combined cord dual element, you could probably only run that single element up to 12, 13, maybe 14 degrees angle of attack, whereas the combined angle of attack of a dual at the same cord could probably run up closer to 25 to maybe even 30, depending on the design of it. Yeah, so that's why you see Formula One wings where the flap is almost vertical. We do the same thing on autocross wings. You can get a ton of combined angle of attack because you renew that boundary layer, and now you've got the flap with perfectly attached flow, and you can really, really make that flow shoot straight up kind of thing. Yeah. Okay. Yeah, whereas that just would not happen. That wouldn't happen with a single element because the boundary layer has already built up too thick, and so you can't ask the fluid to change direction that drastically at that point. Gotcha. There's a lot of other very more complicated aspects of dual element design, be it flap gap and overlap and the flap camber and all of that, but that's probably well beyond that's the master class chat. That's probably for a different day. I noticed on the new bringing it to GT cars, on the new GT3 RS, it has a dual element wing that has DRS. Why would somebody? What does DRS do? It's a drag reduction system, DRS. So dual elements are amazing for generating a lot of downforce at a much higher combined angle of attack, but typically they're going to make more drag, unless you're very, very low angle. So we can maybe show a graph here showing that, but very basically, to make more downforce, you have to make more drag. There's no such thing as free downforce. Sure. So if we want to get the top speed that people want out of a GT3 RS, because that's what sells cars, then you have to reduce the drag some way. And by opening up that flap gap or reducing the flap angle, you're reducing the drag and the downforce at the same time. But it's a very effective way to do that.
Got it. Wing end plates. This is another one that there's a bit of flattery as of late. If you've been following along on the Dundon Zebulon partnership, the Valkyrie wing that was birthed of that cooperation has very beautiful and functional end plates, and we've recently seen them again being used by another Porsche tuning shop, almost surprisingly blatantly so, to the extent that when I sent you the picture, you're like, "Are you serious?" But they're much bigger than us, and that's really cool. It's kind of maybe they got to the same place, because it's not. I will say it is rocket science, or at least aerodynamic science, to come up with those shapes. But let's talk about why the end plate is important on the efficiency and function of a rear airfoil.
The end plate is super important, yes. So on an airplane wing, you have this really crazy long span where the wing can function very efficiently over a large majority of its surface. On a race car, for an airfoil, the span is relatively narrow. So we call that aspect ratio, and race car wings have really poor aspect ratio. So we get a lot of losses from the high pressure zone on top of a race car wing wanting to travel towards the low pressure zone. End plates are a way to try and control the wingtip vortex that results from that flow differential and that flow movement.
Okay.
So,
so like, kind of where it would spill over from on the edges, where it would want to spill over and kind of combine from that differential pressure. You're trying to guard against it from spilling over. Okay. Yeah.
It's every low pressure or high pressure wants to move towards low pressure. Period.
There you go.
Think about it. The weather.
Going downhill.
High pressure systems. High pressure systems move towards the low pressure systems. The high pressure on top of a race car wing wants to move towards the low pressure. If there was no end plate, you get a really tight vortex that forms right at the wingtip, wingtip vortice. And so we just want to try and control that flow as much as we can. You're never going to get rid of that vortex. So if we use it to our advantage to try and maximize what the wing is doing, then we can increase the efficiency and function of the wing. So you mentioned someone kind of copying the design of the Valkyrie. It's not that unexpected, because certain shapes just tend to work. And
right.
So it's just one of those things.
A good shape. I mean, it'd be like saying somebody copied the shape of a wing, right? It's like being able to optimize for the same answer. If you know what you're doing, then given same boundary conditions and the same problem definition, you're very likely to get to a similar end result, in both shape and function and design and these kinds of things. So certainly not trying to accuse anyone of just copying our homework or anything like that. That would be silly. But the striking similarities between the two were affirming in some ways. It's like, oh, well, that's kind of cool.
Sure. Imitation is a very high form of flattery.
Absolutely, 100%. Even if it's complete coincidence and wasn't copied at all. What is in specifics, you've got some wings that, like the stock GT car wing ends are just very straight and kind of thin. They don't look like they would be trying to keep the upper flow field and the lower flow field separated very well. On the Valkyrie wing, it's much taller, and it has subtle curvature in it. Can you talk about what that curvature at the bottom of it is trying to achieve?
Well, so it's very three-dimensional. The only place that there's any flat surface on that end plate is where it actually bolts to the wing.
Sure.
And it's apparent when you look at it, and it's very on purpose. We're basically just trying to maximize the increase in speed underneath the wing element, dropping the pressure more. We're trying to control how the wingtip vortices form and where they're traveling, so that we can create effects from the end plate that we would get from a larger, just flat end plate. And so we can get a much more efficient package that way. Mm-hmm. And it's even a little bit airfoil profile, so there's a little bit of trickery to that, where we're getting some performance out of the upper and lower surfaces of the wing from the way the end plate is shaped.
Gotcha.
And all that. So yeah, and then
again, it's the 1 + 1 = 3 kind of situation in aerodynamics.
Sure.
Yeah.
Sure. And then it's not a sharp edge anywhere on that end plate. So we're not
sharp edges are bad. Why?
Sharp edges are bad because typically, unless the flow is hitting it directly straight on, it'll separate, and so then it'll have to reattach, and you're wasting energy. You're imparting energy into the airflow, and that's draggy.
Gotcha. Yep.
Yeah.
Perfect. Materials used in aerodynamic wings and spoilers. So this is gonna be a dovetail for a conversation with one of our carbon manufacturers at some point. There are effective ways to build these aerodynamic devices, and the most widely used material for this is carbon fiber. And can you explain why is carbon fiber generally used in these applications? There are, of course, exceptions, people using aluminum for aluminum wings and these kinds of things, but talk to me a little bit about why carbon fiber is generally seen as an aerodynamic material of choice.
It's not just an aerodynamic material of choice. It's just a very high specific stiffness material. It's very strong for what it is. It's very light for what it is. And it's, once you have a moldable into essentially any shape you want, which is important for a designer like me, where I want to make very specific shapes to force the airflow to do specific things. Yep. So it is most certainly the material of choice. It's not the cheapest material of choice, but it is the most effective material of choice for this type of application in my eyes.
Right on. I agree. There are other materials that can be used, and in some instances they're I'll say similar to carbon fiber, but when we're talking about carbon fiber, we're literally talking about pre-preg molded, cured carbon fiber that's allowed to be put into a shape. It's allowed to be have internal structure that you can use to beef up the loads that a shell of a carbon fiber part might not be able to handle on its own. These kinds of things like ribs in wings and such like that to carry the load and make them strong. Hence, 3 men and a dog or these kinds of things can stand on it as it sits there, because at 150 miles an hour and it making 1,000 pounds of downforce, you damn well should be able to stand on it without fear of cracking, breaking, et cetera, or you're very likely to crash a car.
I don't want to see failures anytime.
Right.
You're always running a risk of something happening when you're doing a dangerous activity like racing a car.
Sure.
But we don't want wing failures. We don't want splitter failures. Nobody wants that. And carbon fiber is the material that, as long as it's built appropriately, the material that is going to make the best part for that.
Right on. Are aerodynamic parts model specific or universal? This is a rabbit hole of a question but
totally. So they can be model specific, or they can be universal.
Sure.
For the designs of the Valkyrie, they're not model specific, but they're very close to it because the P car shape is very unique, and so that shape is tuned to the 911 and the Cayman body shape and flow field.
The rear windscreen angle on both cars are very similar to one another. The roof, how it falls away, what's kind of happening in the deck lid area of the car, very similar between the two. So we can apply what we'll call a universal wing for us. For Dundon Motorsports, we only play with Porsche GT cars for the most part. So we can apply it to those shapes more universally, because it, quite honestly, is a specific wing design for that roof, rear windscreen angle, et cetera, et cetera. It was all kind of accommodated for that.
Yeah. So if you're talking about like putting a wing on an Acura Integra or on a Galant VR4, like a 90 Galant VR4, that's like super boxy. Right. The flow field is going to be so different between all these different cars, and it's three-dimensionally different. It's not just as viewed from the side, but even as viewed from above. It's all three-dimensionally different. You have flow approaching the wing at different attitudes and different angles all over the place. So sometimes it's just simpler to do a straight wing element. But when we have data and we have a very specific target, like the P cars for Dundon, we can alter the profile shape and the profile size and the static angle of attack as you move across the span of the wing, all to try and maximize the performance of the wing for that application.
Right on. That's actually the graphic that you have next. Let's talk about that. As we add a wing to most of the GT cars that we're playing with come with a wing from the factory. Why should I upgrade it to a Valkyrie wing? What do I get?
So the GT cars from Porsche are still road cars, and they're designed to be road cars. Right. So they are designed to be relatively safe, and they're really looking to make reasonable levels of downforce. They're trying to get that big step from the lift that normal cars generate to a little bit of downforce. Yeah.
Sure. Yeah.
So, that there is a reason that a GT3 is a very fast car. There's a reason. But that doesn't mean that we can't do better. We can do significantly better. And if you want to maximize the performance of your Porsche, like, there's a relatively easy way to do that, and that's upgrade the aerodynamics to something that would be more akin to a bit of a racier setup. Like, we're just trying to do more.
Right. One of the things that I find talking to customers about the parts, and a great example of this is the YouTube video we did with the 4RS with all of the bits on it, and we did suspension upgrades, and we did, some other things with it. But we would take guys that had driven the car stock, and these are amateurs all across the spectrum, from Ted, who's our sales manager and a pro driver, still very highly competent in a race car, can communicate it very, very well, to, we had, in some cases, almost a 25-second per lap time spread between the guy that was the fastest and the guy that was the slowest in the car. And all of them went 5 seconds faster. Every single one of them went 5 seconds faster with the parts on the car. And that I wasn't expecting. And so when we're talking to customers about it, it's this interaction for a novice driver that, yes, you can take a cargo pilot and you can stick them in an F-16, and they're going to be able to generally fly the F-16, but that isn't going to turn them into a Top Gun just because the F-16 can do it, right? They're going to fly faster than they had in their cargo plane, right? But they're not going to be able to do the things. What it will do for them is it gives them this level of ability and this level of predictability for doing a high bank turn that they could never do in their cargo plane because the plane can do it. Kind of translating that back into the car and a novice driver, you give them the ability to feel the car not doing twitchy things underneath of them that kills their confidence. The car's very planted, it's very normal, it's very predictable, it keeps doing those things over and over and over again, so they're able to find in themselves a faster way to get around the racetrack. Because yes, obviously with a 25-second spread, the car can go faster in the hands of somebody who is faster, but you finding the confidence to explore going fast in a way that you haven't done before is part of the reason to upgrade the car. It's not just that the car goes faster, it's easier to drive fast, right? And that's part of the reason why you might want to upgrade your car. It isn't that you shouldn't also work on the driver mod. It's because if the driver mod, if the car isn't doing crazy things, and the GT4 RS stock does all kinds of crazy things that shake your confidence as you're trying to go around the racetrack. So doing anything to make it calm the down and just do the things I'm asking you to do, not the crazy things that you want to do, crazy chassis, McPherson strut, bump steer, curve, blah, blah, bullshit, is the point, right? That's kind of why we started doing this, is to both enhance the performance envelope of the vehicle and to make it more accessible to the driver.
Yeah, I would agree with all that. And, you know, the Caymans are a little more of a difficult car to drive than the 911, and adding some grip to the car increases drivers' confidence significantly. And yeah, there is a learning curve to aerodynamics, specifically how to drive the car with that. But if you're more comfortable, especially in a car that's a little harder to drive like a Cayman, it can make for a much quicker lap time and a more enjoyable experience. I mean, and that's just different cars are that way. Not every car is going to be 5 seconds, but it's certainly possible. And obviously, I mean, you guys empirically showed it. So
yeah, which is just nice to see. The GT3 RS may be a little bit more of a challenge to try and find meaningful improvement on, but we're up for the challenge. I'm interested to see what we can do with it, because to your point, Porsche makes road cars, and every road car has their specifications driven around operating on the road, not exclusively operating on a track surface. So that, and
if you
go ahead.
I was gonna say, if you change anything about the car that Porsche designed, even down to the tire size, like just if you get a tire with a different section width, there's changes to the way the car is going to perform, and it's not going to work as designed by Porsche. So
we talked about this early on, because like the GT4 RS and the other Caymans come with 245 series or 245 wide tires in the front. And most people want to increase their width to 265 to have more contact patch, bring more mechanical grip to the front of the car, blah, 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 all that good stuff. That's a different topic for a different day. But when you do that, like we were talking about, the air curtain that is used on the side of the car to try and do a little bit of what a dive plane might try to do more efficiently is completely out the window. So now you're driving the air curtain right into the tire, donk, and it does nothing. Right? It doesn't go around the tire anymore. So
yeah. And air curtains are very small. They're low effectiveness, but they are effective, and they reduce drag. They can increase front downforce a little bit. But yeah, when you change the tire width, it doesn't function the way that it's intended at all. So that's the reason that we took that outer piece off on the GT4 RS and decided to run dive planes there instead.
Right. Let's talk about, let's see, we've got benefits of a front splitter and underbody. Ground effect and its role in aerodynamic performance. These are a little bit of buzzwords. Some of
Sure.
them, ground effect. People, like I very often have to correct Cup car owners that their car has a splitter on it. Like, your car doesn't have a splitter on it. It has an air dam on it. They are different aerodynamic devices, not necessarily doing the same thing. Can you talk a little bit about, definition and what the difference between those things are?
Sure. I mean, it's like a Cup car lip, the little air dam, the plastic piece that we lose at every single race. That is a splitter. That is a splitter in that, yes, it does split the airflow.
Sure.
Yeah. But it's more of an air dam. It functions more like an air dam, and more so on a 991 Cup than it does on a 992 Cup. The 992 Cup has a little bit of bottom section to it.
Okay.
But then the airflow just separates off of that, and it's really trying to make downforce by forcing as much air over the top of the car as possible.
Yeah, like sealing it against the ground,
nose.
so to speak.
Yeah.
Right?
Yeah. So that's how it functions, more like an air dam. When we replace something like that with a true splitter, then that is not only splitting the airflow over the top of the car and under the bottom of the car, but it is also managing and handling and augmenting the way that flow is traveling around the nose of the car. And when we say ground effect downforce, when we're talking about a splitter, it's not the ground effect that you see in an airplane when you're landing. That's a totally different ground effect. The ground effect that we're talking about is that we're speeding up the airflow underneath the nose of the car because there's a limited area that it can exist in. So we can generate significantly lower pressure by doing that, rather than just it being in a free stream flow.
What's the relationship between a compressible fluid's velocity and the pressure? This is something that is not obvious for probably a lot of our viewers. I understand it, but yeah.
Yeah, it's relatively, it's not linear, but and it
has to be constrained for it to really be a thing, because
yes,
100 mile per hour air has 14.7 psi, the same as 10 mile per hour air if it's just in a free stream, as you stated, right? It's got atmospheric pressure. That's that, right? Yeah.
So, Bernoulli's principle, which is part of how aerodynamics work and how wings work, and it's how ground effect works. So yeah, it's not a linear relationship. And so when you look at one of these Valkyrie splitters, you're going to see it and say like, oh wow, that's so low to the ground. It's really not that low to the ground. It can go a lot lower, but the lower we get exponentially more performance out of it. So it's a really nifty aerodynamic tool.
Sure, because we're using the ground specifically as a plane to squeeze the air and speed it up, right? The thing that I know you were really happy to see was that your splitter design, when we're turning the car, is actually more efficient than when we're just going straight, when the air is hitting it normal, when the air is coming across it in yaw, when we're trying to move the car around, the splitter actually will make more downforce. Can you explain, without giving any of the secret sauce away, why that is?
I don't know that I can explain it without giving away too much secret sauce, but it is very specifically designed to do that. And we did that because cars yaw around corners. That means that it's the total slip angle, the combined slip angle. That's what.
All right. So, what is aero balance, Ryan? Why is aero balance important?
So aero balance is like very important, right? Cars are set up to have a little bit of understeer from the factory and the P cars are set up to have a little bit of aerodynamic understeer as well. And that is essentially the relationship between the center of gravity, or the mechanical grip balance a car has, and where the center of pressure that the car has exists in relationship to each other. So the center of pressure is essentially the average location of the forces being generated by the aerodynamic forces around the car, that average location. So we pretty much it's not a left to right thing that we look at very often. In roll and yaw, maybe we might look at it, but for the most part, we just look at it as front to back, and that will tell you how much additional grip essentially you're going to get from your front tires and your rear tires. So if you have 35% aero balance, we talk about the aero loading on the front axle, 35%. So then you'll have 65% on the rear axle. And, we try to tune that to be safe and also to maximize the drivability. So you want it to be relatively close to your mechanical grip balance, so that it's not changing over the speed range. So if you had a really, really far forward aero balance, which is hard to do, but just for
if somebody just
sake,
puts a splitter on the car and doesn't upgrade the wing, for instance.
So, which is extremely dangerous. That would be, an aero balance of 75-80% front, and as you increase your speed, you increase your aero loading by the square of the speed increase approximately. So you just get more and more and more and more load on the front axle, and then all of a sudden you're in a really dangerous situation where you have way too much grip on the front axle than you do on the rear. So we have to do it in a balanced way.
Okay, very good. I do get the question a lot, hey, my car understeers, I want to add a splitter to the car. And I'm like, whoa. We got to solve this problem more holistically. Yes, your car understeers, but there's other things we can do to help with that immediately. And we can add aerodynamic devices to make the whole car have more grip.
Definitely. So, the mechanical balance is super important. And in that, this ties into the platform control that you have to look for when you add certain levels of aerodynamic loading.
Right.
So as if you're going to go with this Valkyrie package, you do have to kind of account for the extra grip and the extra load that's being put into the car.
Yeah.
If you run the stock springs and you don't account for the extra load at 150 miles an hour, have significantly more downforce pressing the car down, and so
squish it directly into the ground. Right.
Exactly.
Right onto the bump stops, for instance.
And we just talked about ground effect, right?
That's right.
Yeah. And we just talked about ground effect. Well, ground effect is also kind of exponential. So if you have the splitter at 3 inches off the ground, and then the suspension compresses to the point where at 150 miles an hour, it's now 1.5 inches off the ground, it's gained a ton of downforce on the front axle, but your wing didn't do that because it doesn't have any ground effect. So there's a dynamic change in your aero balance because of the inherent design of a vehicle. And so platform control is extremely important. In fact, that's one of the main things we work on in the pro world on these GT3 cars and the GT, the DPIs and stuff is all platform control.
The conversation I've had with folks is, well, if I just upgrade the springs, isn't that enough? I'm like, well, no, because the street dampers don't have enough power to control what you just described as the car, 150 miles an hour and it's squishing, and then you go into braking and you're dynamically changing what's happening in the car. The rear's going to shoot up, the front's going to compress even more because the dampers don't have enough power to deal with it, and now you've got the splitter on the ground, and you have to when Ryan's talking about platform control, he's talking about the weight shift on the car moving fore and aft as you're trying to move it on the racing circuit. So, as you're in transition, that's what I was looking for. As you're in transition, you're not just steady state. Yeah. You're in transition and trying to move the car.
We're never gonna get the car to stay perfectly flat all the time, unless we had hydraulic suspension or something like that. But we at least want to control it to the level that it needs to be controlled at. So.
All right. So product specific questions. We talked about this. Weight of aerodynamic products and their effect on the overall vehicle weight. So Brian already kind of covered this. Carbon parts are light and they're kind of like free extra force without adding more mass to the vehicle that you then have to control when you're trying to change the vehicle's direction. Because the heavier a car is, the harder it is, or the more energy it takes to change its direction. So you want a light car that doesn't require a lot of energy, either from the tires or from the engine to accelerate it, or the brakes to decelerate it, or these kinds of things to help move it quickly and efficiently. OEM parts, performance and quality. I'm going to try and run through these relatively quickly. The OEM parts on a Porsche are generally very good, and this has been the wonderful cooperation between Dundon and Zebulon. So Ryan's role is to design for us efficacious aerodynamic devices. It's our job to mount them elegantly to the car, both so that they're very strong, they're structural, that the forces that the aerodynamic device is going to transfer to the car can take it, things don't break, things don't bend. We don't just drywall screw the splitter to the bottom of the plastic bumper kind of thing. It's supported from the frame rails. I remember some of the pictures, even another funny, an aerodynamic engineer friend of mine asked, because he works on airplanes, how are you standing on that splitter? How does the bumper not come off the car? And I'm like, are you asking a serious question? Is that really? He's like, yeah. I was like, because it's not attached to the bumper at all. The bumper's riding on top of it. There is no part of that splitter that's attached to the bumper. It's attached to the frame rail with nicely, elegantly designed braces and cross braces and et cetera, to hold it on the car, regardless of what the car might experience going around a racetrack. Maintenance requirement for aerodynamic products. That's not one that I would have thought of. Is there a maintenance requirement? Is there a timeout for these things?
You're not going to be getting into plastic deformation or anything on any of these parts.
Right.
I wouldn't imagine. I think you're just going to take care of it like you normally would. The splitters, they're in close proximity to the ground, so you have to keep your eye out on that. But that's why we designed the rub blocks into the system. So you have those outer rub blocks, and then the small titanium pucks at the center for braking protection. So as long as you make sure that you're keeping up with watching those things, I think you're pretty much going to be fine. Don't hit stuff with it.
Yeah, exactly. My guidance to guys is just because you have a splitter does not mean you now have a bulldozer. So don't run into things intentionally. Yeah. It's still a bespoke carbon piece that it's very strong, but you can destroy it if you try hard. So don't try hard.
Yeah, I mean, these parts are designed to the same level that you would find on a GT3 car. So, right. They're going to be able to take a lot of abuse, but if you hit something really hard with a GT3 car, you're still replacing.
You're still going to break stuff.
Wing, yeah. But for the most part, just keep your eye on things, and if there's guys out there that are going to use these things for like real legit racing stuff, and they want to run the car really low and very aggressive, they just got to keep a bigger eye on what's going on.
Yep. Absolutely. Nothing that runs on a race car lasts forever. We'll say it that way. You can eventually break some stuff. Just keep an eyeball on it. It's not a consumable. You're not going to have to. It's not like a brake pad. The pucks are like brake pads. You should certainly be looking at the titanium rub blocks and the outer edge rub blocks, like you said. Make sure that you're not grinding the carbon into the ground. But yeah. All right. Recap of key points discussed. That we may have to film separately because we went over a shitload.
We did.
I would say the going back to the Instagram live we did last week, Ryan mentioned differential pressure a number of times, and that's why I was very adamant to try and help people understand it from the last time, what that means. It's the difference in pressure from high to low. It's that difference in pressure that we're trying to manage in an aerodynamic application, because we have a certain amount of pressure we can build on top of the car from air having mass, and we ideally are trying to elegantly remove as much pressure from the bottom part of the car to make it all, the difference in pressure to be larger. Same with a wing. The difference from the top of the airfoil to the bottom of the airfoil should be large, and then it creates a lot of downward force. It wants to move from high pressure to low pressure. Things, driving forces roll downhill, top of the hill to the bottom of the hill. The ball rolls downhill. The future developments up next. I'll talk about that for a second. We get asked a lot of, why don't you have barge boards, and why don't you have diffusers, and why don't you have all of these other aerodynamic devices? And quite frankly, money. It's just, yes, we could continue to develop the car till it's a 919 Evo for all of you Porsche nerds out there. But we're trying to hit the biggest, most efficacious, and the most cost-effective mods for the car that are easy to install, no modifications necessary, no permanent mod. You don't have to drill holes in the car to put stuff on it, and that have the widest application so that we don't have to charge a gazillion dollars. One of the things that's worked out really brilliantly is we made the splitter so that the splitter blade is modular and can be applied to a number of cars. We only have to change a few things for how it dovetails with the bumper. So we have one mold, one kind of splitter, and because of the more, as far as the air is concerned, the shape of a Cayman and the shape of a 911 and the shape of a 991, the shape of a 987, 981 are all close enough that we can use the same design very effectively without any nuance. Like recently, the CFD on the GT4 RS, Ryan and I were reviewing it, and because of the vented fenders, the splitter works better. And because of the larger diffuser in the bottom of the car, there's more downforce on that car with the full package than there is on the 992 GT3. It's not an enormous
not
amount
a lot,
more, but it's more, right? It's enough so that on CFD you would say that it's more, right? Would a driver be able to tell the difference? Maybe. Really,
I think Ted
skilled?
I think Ted probably would. Yeah. I mean,
Yeah.
it's a reasonable difference.
Right
So,
on.
yeah.
Yeah. Anything else you want to cover before we wrap up?
No, I mean, we just have enjoyed doing this, and like I said earlier, we just like making cars go fast, and I like designing these cool parts. Yeah.
Similar.
Yeah. So, I'm looking forward to any future development that we do, and let's make some more cars go fast.
Let's make some shit go fast. I like it. All right, Ryan, I appreciate your time tonight. As we get this kind of cut together, I'll send you a rough cut so you can kind of take a look at it. We'll probably be in touch for some slides and some pictures that we can add to it.
Okay.
But yeah, this was great. This went really well.
Cool. Sorry, I went down rabbit holes sometimes.
That's good. That's the whole point. That's the whole point. I do the same. You should see me like completely wrap myself around a freaking pole sometimes on the lives. I'm like, why did I start talking about this? No one knows what the hell I'm talking about.
Yeah. It's one of those things, right? But
yep. Engineers engineer, and we forget what a base level of knowledge is required to even have a bloody clue what the fuck we're talking about. right?
Mm-hmm.
So, yeah. All right. Go drink beer. I'm going to go to the Korean restaurant with my brother-in-law and call my wife back and see, hopefully the house isn't on fire. So.
All right. Thanks, guys.
All right, brother. Take it easy. Thanks.